Let's have a look at cross-sections. You might remember that we previously focused only on aspects that were very important to us at the time. Here we can see that it takes 10 to the power of minus 22 seconds at the point of contact, up to 10 to the power of minus 18 seconds for the formation of a compound nucleus, once neutrons have already been emitted in order to cool the nucleus, which brings the collective motion in this direction, with minimal losses, to maximize the output. So far, we have only had the opportunity to trace the movement in theory to this point of capture. I already mentioned that our experiments have received some theoretical description, but up to this point, we only have experimental data, and it would be extremely interesting to move on and understand what would happen in reality. The calculations that were made by Umar and the team showed that the so-called quasi-fission is very dependent on orientation. The polar nucleus is the target located next to spherical calcium, while the opposite is referred to as an equatorial nucleus. Quasi-fission very much depends on the time the nuclei stay together, and from this comes the conclusion that the equatorial orientation is preferable because it will lead to a compound nucleus. And here is the experiment that was carried out. As far as orientation is concerned, this question is absent in cold fusion, because both lead and calcium nuclei are spherical. And here we run into this question. If it is a near-tip or polar collision, then the Coulomb barrier will be small. If it is a near-side or equatorial collision, then the barrier increases. The difference in barriers is 20 megaelectron-volt, which is a pretty decent value. And this is an experiment in which there was a quasi-division, similar to the division of a compound nucleus. But today, when we already have a cross-section for the formation of evaporation products, we can restore the compound nucleus from these products of evaporation. If we restore it, then it turns out like this. If this is the result from the reaction of calcium-48 with plutonium-244, the compound nucleus behaves in this way due to a selection of states. Not only does it move through the barrier, but also the selection of a state occurs, and the compound nuclei barrier that determines the compound state is located right here, resulting in this equatorial configuration. This polar orientation does not create a compound nuclei barrier since it does not reach, but the equatorial does. If someday we manage to create a polarized target, then we can only collect equatorially aligned nuclei, after which we will be able to greatly increase the effect due to the fact that all the collisions will be lateral. Here we can see cold fusion, which lasted up to the 113th element. Of course, there is a clear advantage in using calcium-48, especially on heavy nuclei, especially in the area of superheavy elements, where this difference is about 3 orders of magnitude. This is what the nuclei look like on the island, and this is what the nuclei look like on the continent. Here we have a rather large cross-section, 10 picobarn. And even if we go to the 118th element, it is about 1 picobarn, while on the continent there is no further development. Here 0.02 picobarns became visible at the 113th element, and this is probably the last one. That is, you can only move forward by crossing the island. The island contains more than 50 nuclei produced by the reactions between actinides and calcium-48. We want to create a bridge between the island and the continent. As we know, there are many different types of bridges, for example, a hanging bridge. as long as we manage to create a connection from this island to the continent. And it is better to make these bridges on the 112th or the 114th elements, because the 112th element is located on both sides. If such a bridge is created without any support, then, figuratively speaking, you should still be able to reach the 112th element, which is on this side, with the help of calcium-48. This would mean that there is a suspension bridge, that is, it is necessary to move in this direction and irradiate not uranium-238, but uranium-233 with calcium-48. Then we would get the same nucleus that was obtained in cold fusion. Unfortunately, this approach did not work, and the nucleus was not obtained. After this, we decided to use supports to make the bridge, in which case it made sense to put the support closer to this area. This could also be done with element 114 by taking uranium-239 or 240 and calcium-48. Therefore, in order to move from one nucleus to the next, supports need to be placed in this way. The first support showed a sharp decline in the cross-section of the compound nucleus and a sharp drop in stability. From here, stability dropped by 2 orders of magnitude, and the cross-section dropped by more than 1 order of magnitude. This once again supports the theoretical prediction that superheavy elements are located on the island. There is a fairly deep strait between the island and the continent, and up to now, we have not been able to cross this strait. The theory predicting that superheavy elements are located on the island is therefore very strongly supported.